All right, so continuing with force vibration, all of you are able to see the presentation screen, I hope. Gaurav? Hello?
Yes, sir. Yes.
Have you received the quiz link and today's question?
Yes, sir.
Okay, all right, so we'll start with today's lecture. I'll just do a quick recap. So far we have seen questions in which a uh, sinusoidal or a cosine force is applied directly to the mass, okay, and we derived the equations for this condition, and we also plotted the graph for magnification factor versus frequency ratio and phase angle versus frequency ratio. So we'll continue with few problems on that. So first question for today is I will just read. A 82 kg machine tool is mounted on an elastic foundation. An experiment is run to determine the stiffness and damping properties of the foundation. When tool is excited with harmonic force of magnitude 8000 newtons at a variety of frequencies, the maximum steady state amplitude obtained is 4.1 mm at a frequency of 40 Hz. Estimate the stiffness and damping ratio of the foundation. Alright, so we'll start with the solution. I will just summarize the data. Mass M is equal to 80 kgs, 82 kgs, 82 kg. F0 is equal to 8000 Newton. K we have to find out. Zeta is 1. XP is 4.1 into 10 raised to minus 3. Zeta is not 1. Zeta is what you have to find out. Okay. XP is 4.1 into omega p, that is peak frequency, is so peak amplitude and peak frequency is given twice by fp, so it is twice pi into 40. So now we'll start with the calculation of stiffness and damping ratio. So both you have to calculate, and zeta, stiffness and zeta. All right. Now xp by x0 is equal to, so at when R is equal to RP, so at this peak frequency ratio, this expression reduces to 1 upon 2 times zeta divided by root of 1 minus zeta square. So this we have already derived. So all these equations you need to keep in mind, and x0 can be given as f0 by k. Alright, so substitute all the values. So I get 4.1 into 10 raised to minus 3 divided by 8000 by k is equal to 1 upon 2 times zeta into root of 1 minus zeta square, right? Or k is equal to 975.61 into 10 raised to 3 divided by zeta into root of 1 minus zeta square. Okay, just simplified that. Okay, also peak frequency ratio Rp is equal to 1 upon, sorry, 1 minus 2 zeta square. Okay, so that is equal to omega p by omega n is equal to square root of 1 minus 2 zeta square. Okay, omega p is 251.33 and omega n is equal to k by m, so that is 82 kgs. Right, and that is equal to, and this is equal to 1 minus 2 zeta square. Okay. So k is equal to 5.18 into 10 raised to 6 divided by 1 minus 2 zeta square. So now you have two equations for k. One, this is one equation, and this is second equation. So equate both these equations. So I have equated both these equations here, and so ultimately I get a expression in terms of this zeta, right? So I want to find zeta. So so solve this by using your calculator and get the value of zeta, or or you can simplify this. If you simplify this, this becomes zeta square into 1 minus zeta square is equal to 0.0354 into 1 minus 2 zeta square whole square. So this becomes zeta square minus zeta raised to 4 is equal to 0.0354 into 1 minus 4 zeta square plus 4 zeta raised to 4. So this becomes a quadratic equation in terms of zeta square, and I get 1.1418 zeta raised to 4 minus 1.1418 zeta square plus 0.0354 is equal to 0. Alright. So on simplifying this, I get two values of zeta square. So zeta square is 0.968 and or it is zeta square is equal to 0.032. Obviously, and if you take square root, I get 0.984 or zeta is equal to 0.179. Okay, so this value has to be discarded because this is greater than 1 upon root 2. Alright, so your value should, to get a peak value, you should have a value which is less than 1 upon root 2, or it should be less than 0.707. Alright, or it should be less than 0.707. So you are selecting the value, that is zeta is equal to 0.179. So substitute zeta is equal to 0.179 in the expression for k, and that will give you the value of k, that is equal to 5.54 into 10 raised to 6 Newton per meter. Alright, so that is the value of k. Alright, now go ahead, and so this is just a summary of the calculation. Now go ahead and answer the first two questions of the quiz. Open up your quiz and answer these two questions. Just select the answers, do not submit it. I will give you 1 minute for this. It is 9:18. Submit it till 9:09. Don't submit it, means select the answers, and then we'll move on to the next part. All right, so we'll continue to the next topic. Now, the case which we have seen, in that case, the force F is equal to F0 cos omega t. This force is directly attached to the mass. All right, so if you have a spring mass system, spring mass damper system, right? So this force F of t is directly attached to the mass. Okay, now we'll see different cases which can cause harmonic excitation. Harmonic excitation. Right? So first case which we are going to see is rotating imbalance. Right? So you have a spring mass. So this is done. All right. Now we will see the next case. Okay. So you have a spring mass damper system. And this is attached spring of stiffness K and a damper of damping coefficient C. Right. This is K, this is C. Now on this mass there is an eccentric mass m0 having eccentricity E, and it is rotating in this radius of eccentricity, that is E. All right. So this is the mass is vibrating up and down. Okay. This is your X. Right. And simultaneously this mass is also rotating. All right. So I will draw the free body diagram of this spring mass system at some point of time t. Right. So, forces will be spring force. So this is moving up, and then this mass has moved to some position, angular position theta, and this theta will be equal to omega t. All right, because that is the frequency with which the mass is moving, and this mass is m0. All right. So and you have your spring force here, and also you have there is a damper. You have your damping force, that is Cx dot. All right. Now apply the D'Alembert's principle. So D'Alembert's principle is summation m f is equal to mass into acceleration. So m minus m0 into x double dot plus acceleration of m0. I am writing it separate. That will be d by dt square.
Hello, sir.
Yes.
Sir, how it is means translating and rotating simultaneously?
See this block, big block. Okay, this is translating up and down. All right. Now
Okay.
inside this big block of mass, there is another small mass m0. Okay, and it is located at eccentricity E, like your IC.
Okay.
Okay, like you have your IC engine. So in your IC engine, the engine is will be vibrating up and down, but inside the housing you also have like something like a piston or a crank. Okay, so
Yes.
that is rotating. All right. So this is translating. So mass is rotating as well as translating. Both things are happening.
Okay.
So this acceleration of m0 will be x plus the displacement at instant t. So total displacement, it will be displacement of m0 will be x plus this vertical distance. So that will be e sine theta or e sine omega t. Correct. So that is the derivative, second derivative of that. Okay. So that is, this is nothing but mass into acceleration. Alright, so we are just applying D'Alembert's principle, that is summation f is equal to ma. Right, that is all we have done. Alright, so this is just a summary of what we have just discussed. In between, see, I will keep on writing. You know, if you have any questions, you should interrupt me. Okay. Now we'll write the summation f part.
M,
Yes.
small m.
Small m.
What it denotes? What is small m?
Small m is the total mass.
Okay.
Small m is the total mass. All right. So I will write the summation f part now. Now this is moving up. Motion is upwards. So kx and cx dot are in downward direction. So both will be negative. So the equation becomes minus cx dot minus kx is equal to m minus m0 into x double dot plus m0 into derivative of that expression x double dot minus e into omega square sine omega t. Alright. So I just simplify this equation. So it becomes mx double dot plus cx dot plus kx is equal to m0 e omega square sine omega t. Right? So this is similar to our equation, standard equation, mx double dot plus cx dot plus kx is equal to f0 sine omega t. Right? Where f0 is this value. All right. So our steady state amplitude, if I want to write steady state amplitude of mass, that is x, is given as x is equal to f0 by k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. All right. So substitute f0. F0 is nothing but m0 e omega square, that is the coefficient of sine omega t in the equation. So I get m0 e omega square divided by k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. All of you, please make sure that you are writing everything down carefully, because there is going to be a big quiz on this at the end. All right. So phase lag phi will be given as tan inverse of 2 zeta r divided by 1 minus r square. So we'll simplify this. So this is our summary. Now we'll simplify this. So substitute k as m omega n square. All right. So I'm going to substitute that as, so x becomes m0 e omega square divided by m omega n square upon square root of 1 minus r square whole square plus 2 zeta r whole square. All right. So I'm just going to rearrange these terms, and I'm going to again substitute omega by omega n as r, and this m0 e by m, I'm going to take it on the left hand side. So x becomes m0 e by m is equal to r square upon square root of 1 minus r square whole square plus 2 zeta r whole square. All right. So this is the expression for rotating imbalance. All right. Now I would like to introduce a term, and that term is called as dimensionless amplitude. So in when the force was directly attached to the mass, we use the term called as magnification factor. So for all the further cases, we are going to use this term dA. dA stands for dimensionless amplitude. All right. So this ratio of x divided by m0 e by m for case of rotating imbalance is the dimension amplitude for rotating imbalance. Okay, so this is the dimension amplitude for rotating imbalance. Yes. So this is the expression for rotating imbalance. Right. Any questions before we move on to the next part? All right. So we are going to consider like many such cases. So first case was force f f of t directly attached to the mass. All right. And second case we saw for this rotating. So case 2 is this rotating imbalance case. And we got this expression for this dimensionless amplitude. Okay. Now case 3 we are going to consider for is called as support excitation. All right. So in this case, the excitation is not directly applied to the mass, but it is applied to the supporting structure of the mass. All right. So so we will see how that works out. What case? So case 3, I should write it.
Means
I
what
will
you
just
have to.
explain. I will just explain. Okay. So there is post vibration due to support excitation. Right, so in 1 minute we will see. So you have your mass m and it is attached to the spring and a damper, and this whole thing arrangement is on some kind of a base, and this mass is moving with displacement is x dot is velocity, x double dot is acceleration. But now there is no f0 sine omega t attached to the mass, but instead of that the base or the support is displaced, and the equation of displacement is given as y sine y is equal to y sine omega t, where y will be the amplitude of the motion given to the support. All right. So this is the case for support excitation. Right? So I will draw the free body diagram for the mass. And this is m, and you have x dot, x double dot. All of you, I hope, are writing everything down. There is going to be a big quiz at the end of this section. So unless you have your notes with you, you will not be able to answer it. Okay. So this is the free body diagram. Okay. So y is equal to y sine omega t is the harmonic displacement. Anything that is sinusoidal or cosine wave that is applied to the support, that is called as harmonic. Okay. X is the absolute absolute displacement of mass m. Okay. So x minus y is the displacement in spring, and x dot minus y dot is the velocity of damper. Alright, and that is how we got this forces k x minus y and c x dot minus y dot. just to summarize what we have done. Now apply D'Alembert's principle. Apply.
So which case is this? First, second, third.
Third case for
Okay.
support excitation. Apply D'Alembert's principle. Okay. So summation F is equal to mx double dot. Alright. So that becomes minus k, that's x minus y minus c into x dot minus y dot is equal to mx double dot, or I get mx double dot plus c into x dot minus y dot plus k into x minus y is equal to 0. Alright. Now take all the minus terms with y on the right hand side. So this becomes mx double dot plus cx dot plus kx is equal to cy dot plus c plus k into y. Okay. And substitute for y is equal to y sine omega t in this equation. So this becomes mx double dot plus cx dot plus kx is equal to c into y into omega into cos omega t. So this is nothing but I have taken the derivative. This is y dot, alright, plus k into capital Y. Okay, let me differentiate this. This is capital Y. Capital Y represents the amplitude. K into capital Y sine omega t. Alright. Now I am just going to make some arrangements on the right hand side. So right hand side I am just writing it. This is equal to y, and I am going to divide and multiply by this term k square plus c square omega square. Okay, so this becomes c omega upon root of k square plus c square omega square cos omega t plus k divided by square root of k square plus c square omega square sin omega t. Alright. Now these terms which are in the coefficient, this I am going to write it as these terms. So this will I am going to write it as sin alpha, and this one I am going to write it as cos alpha. Right. So this equation becomes, so RHS becomes y into square root of k square plus c square omega square into sin alpha cos omega t plus cos alpha sin omega t, whole thing into bracket, where sin alpha is c into omega divided by k square plus c square omega square, and cos alpha is k divided by square root of k square plus c square omega square. So right hand side I can write it simply y into k square plus c square omega square into sin omega t plus alpha. Alright. Now again we can compare this whole thing. So our equation becomes mx double dot plus cx dot plus kx is equal to y into square root of k square plus c square omega square into sin omega t plus alpha. Alright. So this is nothing but similar to our form. So this term, I can write it as f0. All right. This term I can replace it as f0. Any questions so far?
What about the remaining two cases?
What remaining two cases?
Case 1 and case 2?
Case 1 and case 2 is already done.
Okay. Your speed is too fast.
Your case 1 and case 2 has been done in the last lecture.
Okay, okay.
What is case 1?
No, no, I have not seen this.
No,
I
you are
don't
not listening. I think you are not listening. Yes, anybody? Varshil, what is case 1?
Force damping.
Yes, and what is that example?
Sir, we are applying force F0 so that frequency will take.
And where is the force applied?
Sir, on the mass.
Okay, and then we saw case 2. What was the case 2?
Sir, today in the previous lecture, means in the
Previous,
beginning of the lecture, harmonic
yes, rotating, rotating
rotating
imbalance,
imbalance.
right?
Yes,
Right.
sir.
So case 1 and case 2 has already been done. Now this is case 3.
know. Okay, sir.
Alright. Anybody else has any other? I hope everybody is in tune with the content.
You go bit slow because it's going too fast with all the quiz and other stuff.
Yes. Okay, like how?
Yes, sir, yes. We are
All right.
not
Like
giving.
which? So do you want me to repeat this section?
No, sir, it's okay, but for like from the next lecture a bit slow because we have around 20 questions in each quiz.
Yes. But these are
Either
all true or false question.
yes, sir. So also we get only 2 or 3 minutes for 4 or 5 simultaneous questions.
It should not take 4 or 5 minutes. It should take like few seconds. It's just reading and interpreting.
So,
Not
sir,
too.
can we keep the quiz at the last
So it
together?
is
You
it
can.
is going to be at the last, na? Only 2 questions have been given of the 20 questions. All right, remaining is will be on the entire content which have been covered so far
Yes,
at
sir.
the end.
Okay, sir. But sir, can you please go bit slow?
Okay, like which part you want me to go slow? Like
No, sir. For now it's okay, but you are going bit fast, so we can't understand each and every segment.
ah, okay, so which content have you not understood?
No, sir.
Are you,
For now it's okay, but
okay,
the quiz and
this
other
speed is
stuff
okay,
it's
na?
yeah. This is okay.
Okay, all right. So now what will be the next step? So in the previous two examples, that is one where force is attached directly to the mass, and the second case where the mass is where there is rotating unbalance. For both these force vibration cases, we derived the expression for steady state amplitude. Now for deriving the steady state amplitude, when we get it in this form, mx double dot plus cx dot plus kx is equal to f0 sine omega t plus alpha, then we can directly write the expression for steady state amplitude, which we have already derived. And the expression for steady state amplitude, I hope everybody is able to recollect this, is x is equal to f0 by k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. I hope this is not new for you, right? Now what is f0 in our case? F0 is nothing but y into square root of k square plus c square omega square. Alright. So substitute f0 in this expression. So you get x is equal to y into k square plus c square omega square divided by k, and that is divided by square root of 1 minus r square whole square plus 2 zeta r whole square. All right, now take k inside of this bracket. All right, so the numerator term k square plus c square omega square by k. I am just going to write it by taking everything under the root. So this I can write it as 1 plus c omega by k whole square. Alright, is that understood? Alright, can I continue? Any questions on this page? Alright, now c omega by k, I can write it as c is equal to 2m omega n zeta, that is c into omega divided by k, that is k is nothing but m into omega n square, and this reduces to the form 2 times zeta into omega by omega n, and that is equal to 2 zeta r. Alright, so the numerator term, the square root term divided by k, it reduces to 1 plus 2 zeta. So this c omega by k, I am going to replace it as 2 zeta r. Alright, so this term becomes, alright, so the numerator becomes x, taking y on the left hand side, becomes square root of 1 plus 2 zeta r whole square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Alright. Okay, so we have got this again, the expression for steady state amplitude. So x is your steady state amplitude. Alright. If things are going fast, you should let me know immediately. And y is the amplitude of excitation applied to the support. Alright. Okay. Now let's use the part which we have already used. Okay. So when the force, when we did this example, we have a mass, and to this mass you have a spring attached to it, and you have a damper attached to it. Alright. This is k, this is c, and to this a force f of t is equal to f0 sine omega t was attached. Okay, so we have discussed this. This was our first basic case. Okay, so in that case, the steady state response for this case was x sine omega t minus phi. Alright, I hope you remember that. Alright, where phi is the phase lag. Alright, now in our case, we have the case where on the force applied is to the excitation, equivalent expression is f is equal to f0 sine omega t plus alpha. Alright. Okay. So our expression is f0 sine omega t plus alpha. So instead of omega t, there is this additional term alpha, which is present in the equation of the applied force, equivalent applied force. All right. So now instead of the writing, so our steady state response, with amplitude x. So x is the steady state amplitude, and the function of time, that is steady state response x of t will be x, that is the steady state amplitude, into sine. So again this term will come omega t plus alpha minus phi, where phi will be the phase lag. Alright, or I can write it in the form x sine omega t minus phi minus alpha. Alright, so this is the expression for your steady state amplitude. Right, so this is the expression for steady state steady state response. Right. So now if you see your example, you have a mass, okay, and this is moving with x is equal to x sine omega t minus phi minus alpha, and it is attached to a spring and a damper at the support, and the support is moving with y is equal to capital Y sine omega t. Alright, and the response of the mass, that is x, will be capital X sine omega t minus phi minus alpha. Alright. Alright. So from that you should be able to conclude the phase lag between the support excitation and the steady state response now becomes not phi, but it becomes phi minus alpha. Alright, so the response lags the support excitation by the angle phi minus alpha. Alright, and to derive this angle, so phase lag, anything not clear, you should interrupt me immediately. Phi minus alpha, so phi
Sir,
is, yes.
sir, last point not clear.
Alright, see, now we have solved this example of mass attached to a spring and a damper, right, and this is moving with displacement x, velocity x dot, acceleration x double dot. This is k, this is c, it is fixed at one end, and to this mass you are attaching this support which is directly attached. F of t is equal to f0 sine omega t. Alright, that is this value. Alright, so when this was the case, the steady state response was what? Xt, that is this term, that is equal to amplitude x sine omega t minus phi, right? Okay, so when the force applied is f0 sine omega t, the response lags by angle phi. Okay, now here the equivalent harmonic, in this case the equivalent harmonic excitation force is what? f0 sine omega t plus this alpha term. Is that clear?
Yes, sir.
Alright, so now here you have this additional alpha, so the steady state response is what? If you compare this solution, whatever is this angle, you are going to subtract the angle alpha from it. You are going to subtract the angle phi from it. Alright, so this the steady state response is amplitude x sine omega t plus alpha minus phi. Alright,
Yes, sir.
and then I have just rearranged this mathematically so that I should be able to write it in the form of omega t minus something. Alright, so these two things are same.
Okay, sir.
Alright, so now see what is the, so now our case is what? You have a mass m which is moving with x, or I should write it, let me write it as x of t is equal to capital X sine omega t minus phi minus alpha, right? This is all the for the mass. That is what we have derived here. right? And this is attached through a spring and a damper to the support, and the support is moving y of t is equal to y, capital Y, sine omega t, right? So here there is only omega t, here there is omega t minus phi minus alpha. Earlier it was only minus phi. So now the phase lag between the support excitation and the steady state information, steady state response is not phi, but for this case it is phi minus alpha.
Yes, sir.
Okay.
Yes. Sir, but how will the support move? It is because of support that the mass is moving. So how will both move? Support move. Support
See,
needs to be stationary, no?
see, support moves means what? See, suppose, see, you have a road, all right? Okay, you
Yes.
have a road. Okay. Now, if you are traveling on a plain road, and if this mass is moving, all right, then there is no disturbance. Only whatever is disturbance in. Right? Suppose you are moving on a plain road, all right, and you have a mass and a damper, okay, and this whole arrangement is moving, all right, and this there is this machine that is vibrating, okay. So now here there is no disturbance that is been provided by the base, right? Now let's take an example where this road now is not straight but it is wavy, all right. Now you have this machine mounted on it, and you have a spring and a damper, and this mass is now moving on this wavy road, all right. So from the base also it is getting this disturbance in addition to the inherent vibration of the machine. Got it?
Yes, sir.
Okay. Or it can be, see, it can be a machine which is mounted on some base, and the base has some other, there are many, one more machine kept on this base, and this machine is vibrating. All right. For example, if you go to your workshop, you have a shaper machine on the floor. Simultaneously, you also have your lathe. All right. So both are inducing vibrations on the floor. So one becomes the source for other for the base excitation. Is that clear?
Yes, sir.
All right. So all right. Any other questions? Okay. So we were on this phase lag. So phase lag is phi minus alpha, and phi is tan inverse of 2 zeta r upon 1 minus r square, and alpha is equal to tan inverse of c omega by k, that is equal to tan inverse of 2 zeta r. All right. So phase lag becomes tan inverse of 2 zeta r upon 1 minus r square divided by tan inverse of 2 zeta r. Any questions? Can I continue?
Yes.
All right. Now, whatever we have derived so far, this is in terms of absolute amplitude. So, x is the absolute amplitude. So, now let me redefine some terms, and let me call this as relative amplitude. All right. So, relative amplitude z is equal to x minus y, and z dot will be x dot minus y dot and z double dot. So this is velocity, sorry, and acceleration. So x double dot minus y double dot. Alright. So I can write x double dot is equal to z double dot plus y double dot. Alright. So the equation for support excitation is mx double dot plus c into x dot minus y dot plus k into x minus y, k into x minus y is equal to 0, right? So this becomes m. So substitute x double dot in this equation. So this becomes m into z double dot plus y double dot plus c. So x dot minus y dot becomes z dot. So c z dot plus k into z is equal to 0, and so I get mz double dot plus cz dot plus kz is equal to minus m into y double dot, and that is equal to m into y omega square sine omega t. Alright, so this becomes again of the form m, our standard form, which is mx double dot plus cx dot plus kx is equal to f0 sine omega t, where f0 is this coefficient of sine omega t, right? So the relative, so now earlier I have derived the expression for, steady state amplitude. Now this is in terms of relative amplitude. So now we will derive the expression for steady state, not absolute amplitude but relative amplitude, using this equation. Alright, so this becomes m into omega square y sine omega t. Alright, so this becomes the steady state relative amplitude, that is z is equal to f0 by k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Alright, so substitute f0 is equal to m omega square capital Y. So z becomes m omega square y into k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Alright, so I can write it in the form z by y is equal to m by m omega square divided by k upon square root of 1 minus r square whole square plus 2 zeta r whole square. Okay, so k is nothing but m omega n square. So when I substitute this becomes omega by omega n whole square plus the same thing which I had in the denominator. So this equation becomes simplified into the form r square divided by square root of 1 minus r square plus 2 zeta r square whole square. And if you remember this equation is exactly similar to the rotating imbalance case. Alright, is everybody able to recollect that? Any questions? Alright, so now the equation of motion is mz double dot plus cz dot plus kz is equal to m omega square y sine omega t, and this is your f0. So the steady state response in terms of relative amplitude. So relative steady state response will be z sine omega t minus phi, where phi will be the phase lag, and that is given as tan inverse of 2 zeta r upon 1 minus r square. Okay. Now let's place this both these derivations side by side so that it is easier to remember. All right. So for support excitation, and so this part is for support excitation and this part is for rotating imbalance. All right. So this is the dimensionless amplitude for support excitation, and this is the dimensionless amplitude for rotating imbalance. All right. So now let's compare this. So Z is the relative amplitude, that is steady state relative amplitude. X is the steady state amplitude for rotational imbalance, and Z is for support excitation. Y is the amplitude of the support excitation source, and m0e is the rotational imbalance, m is the total mass. Okay. This expression is called as the dimensional amplitude for rotating imbalance. This expression is called as the dimensionless amplitude for support excitation. Is this distinction clear?
Yes, sir.
And for both we get the same expression, that is r square divided by square root of 1 minus r square plus 2 zeta r whole square. All right. Okay, so what we'll do, we'll stop for today. The just make a note of the first two questions you answered in your quiz. Okay, so what I will do, you can just go through. So your quiz, which is the next quiz, remaining, so 20 questions are there in the quiz. 2 questions you have already solved. Okay, plus there are 18 questions. So these 18 questions are based on the things which I have covered in today's lecture. That is for f is equal to f0, that is for 3 cases. Case 1 where it is directly attached to the mass, case 2 where it is rotating imbalance, and case 3 is your support excitation. All right. Okay, so on all these 3 cases your next 18 questions should be asked. So that we are not going to do in today's lecture. So what I want you to do is go through all the material that has been covered for all these 3 cases and be prepared for answering the questions. There are some minor derivations that are remaining, so that I will cover at the beginning of the next lecture, and then we will continue with the quiz. Is that okay?
Okay, sir.
All right. So today we are not going to do the remaining 18 questions of the quiz. Make sure you make a note of the first 2 questions, whatever answer you have written. You will have to enter the same answers again for tomorrow's lecture, and then you can submit the quiz with the remaining 18 questions. Is it clear to all?
Yes, yes.
So go through the entire material for case 1, 2, and 3. I will just take the attendance before we end the lecture. Yes.
Sir, for 2 questions we have to submit.
No, don't submit. Just
Okay.
in your notebook, you just make a note, because the same question will be there for tomorrow also. So no need to submit it today. Tomorrow you can submit it. Any
Hello,
other?
sir.
Yes, go ahead.
Sir, for B2 batch, can you upload the presentation of the second experiment?
I mean the write up, na, but you have written it in the presentation format.
No, sir, we have not written anything because you said that you would give the presentation and we have to
Yes,
follow
yes,
that format.
yes. I will give the presentation. Then you can upload.
Okay,
Anyway,
thank you.
tomorrow is not the deadline. I will give you one more week.
Okay,
Okay,
sir.
thank you.
So
Yes.
for the first practical of simple pendulum, can we write the values we have get
Yes, yes.
in
You
the
have to write the
table?
value. Yes.
No, no, no. I am asking that the table in the write-up only.
Yeah, can you can use the just a minute.
Excuse me, sir.
हे माझं लेक्चर चालू आहे मी 2 मिनिटांनी कॉल करतो.
Excuse me, sir.
Yeah, go ahead.
Yeah, sir. Due to some error, I accidentally left the meeting during towards the end of the meeting. Something happened and the thing closed. The
Yeah,
Microsoft Teams.
anyway, I am not we are not going to do the quiz today. I have kept the quiz for tomorrow. All right. So for tomorrow's quiz, remaining 18 questions you have to solve.
All right. Okay,
And
sir.
just go through the entire material which has been covered on
Okay.
post vibration till now. Okay. You should be
All
able
right.
to construct. See, I have showed you how to construct the graph for what do you say for when the force is directly attached to the support, right? So similar
Yeah.
graphs you should be able to, that is the dimensionless amplitude versus frequency ratio, you should be able to interpret. Okay,
All
we are
right.
going to discuss it in tomorrow's lecture also, but based on whatever we have discussed so far, you should be able to construct the what is it, the graph because you need to imagine how the response is, and based on that you have to what is this solve the quiz.
Sir, my issue was like, if will I get like today's attendance because my meeting got accidentally left out.
You are
Indeed.
attended, na?
Yeah, I had attended throughout,
Yeah,
but in the end I left
that is
accidentally or
okay.
something.
You again joined it, na? I have
Yeah, yeah.
the sequence recorded.
All right.
All right.
Sir,
Any other?
for the
Yes.
first practical, means it is okay now if we use a table in the write-up.
You have to use the table. You have to take the printout of the write-up and
Yes.
fill in all the values by hand.
Okay.
Whatever write-up I am going to give you, you have to take a printout of it, or you can take one printout and rest of it can be Xerox. I don't know how the Xerox situation is right now. So best option is to take a printout, and then you have to fill everything in that by pen. Fill the entire data, that is table, your calculations, all these things you have to fill it by pen. You have to preserve the original write-up, all right, and
Okay.
submit the scan copy of the write-up.
Okay, sir.
Any other questions before you end?
So both the experiments you have to submit next week.
Yeah, you can submit it next.
Sir, can we leave?
Yes, yes, yes. That is what I'm asking. If everything is, if there are no more questions, those who want to leave can leave. If anybody has a question, you can wait and ask. I have already taken down the attendance. You can leave. You're free to leave.